Welcome to the new video in Discrete Math series. In this we are going to talk about proofs of equivalence, proofs by counterexample, and some common mistakes we make while doing the proof, right? If you are new to the channel, please do subscribe to keep watching the interesting and good quality videos. Proof of equivalence. So what is proof of equivalence and what is the point that I want to highlight here? Sometimes it may occur that we may come across a situation where we may ask to prove that there are two statements P and Q and they are equivalent to each other. Like means there may be a situation where we have to prove biconditional kind of a statement. Biconditional means that P implies Q and Q implies P. So to prove this biconditional kind of a statement, we use this approach which is based on this tautology. I think in our previous videos we have proved that if I have to prove that P if and only if Q, this is how you read it, P if and only if Q, or you read P if Q, IFF, P if Q. So to prove P if and only if Q, we have to prove that P implies Q and we also have to prove Q implies P. And this is the mistake sometimes you make, that you just prove one part of it and you ignore the other. Now here we have a result which I want to highlight to get the context clear, that if n is an integer, then n is odd, and if and only if n square is odd. So I want to make you understand that there are two parts of this result. First is that n is odd, then n square is odd. Second part is n square is odd, then n is odd. Means this is also said as necessary and sufficient condition. So to prove this, we have to write the proof in two parts. What is the way to prove it? First part we have to prove that let n is true, right? Or sorry, let me rephrase it. It should be like let n is let me rewrite, let n is odd, right? This is the first assumption, and following a set of steps we have to show that n square is odd. And I think this you can do it yourself, because in previous videos we already have discussed about how to prove this kind of thing, that if I will start with n is odd and I will show that n square is odd. This will be the first step. Second step will be that I have to prove V, or let me write V, also need to prove that if n square is odd, then n is odd. So we have to prove it both way. Starting with n is odd, we have to prove n square is odd, and then starting with n square is odd, we have to prove n is odd. But the important point that I want to highlight here, that to prove this result, you can use any method of proof. You can use direct proof or proof by contraposition. So I believe that it will be easier for you to prove this by method of contraposition, right? Again, if you have not understood what is this term method of contraposition, then please watch the previous videos in sequence, right? So I leave this for you to complete, that this you can, for this part you can write the direct proof. If n is odd, then n square is odd, and to prove that if n square is odd, then n is odd, you can use the method of contraposition. Okay, so please do it. Sometimes we also may have to prove the equivalence of multiple statements. Like suppose we want to prove that P1 is equivalent to P2, P2 is equivalent to P3, and P3 is equivalent to P4, and so on, and it is equivalent to Pn. So to prove the equivalence of these statements, we don't have to individually prove that P1 is equivalent to P2, P1 is equivalent to P3, P1 is equivalent to P4, and so on. That will be a very difficult thing to do, right? So what is the right way to prove the equivalence of n statement? So what we will follow, we will write that P1 implies P2. This is what I will do. to prove the equivalence of this, I will write P1 implies P2 and I will prove this. Then I have to prove that P2 implies P3. Then I have to prove that P3 implies P4, and we create a chain, we create a sequence, and in the end we reach to Pn, and then we show that Pn implies P1. So basically we create a cycle that P1 implies P2, P2 implies P3, P3 implies P4, and finally Pn implies P1, right? So if we are able to create this, then we can conclude that all these n statements are equivalent. To understand this, let us take an example. So here we have three statements. That first statement is P1, that n is even. Second statement is that P2, n minus 1 is odd. And third statement is P3, which is n square is even. So what we have to do? First we have to show that P1 implies P2. Then we have to show that P2 implies P3. And then we also have to show that P3 implies P1, right? So let us do it quickly. First, I take let n is even. I start with P1. Let n is even. So it means what? That it means n is equal to 2k for some integer k belonging to z. So this implies what is n minus 1? N minus 1 is equal to 2k minus 1, which can be written as 2 times k minus 1 plus 1. So since n minus 1 can be written as twice of something, twice of some integer plus 1, so we can conclude that n minus 1 is odd, right? What is the next thing we have to do? We have to start with that let n minus 1 is odd. And what we have to do? We have to show that n square is even, means we have to show that P2 implies P3, right? So if n minus 1 is odd, n minus 1 will look like something like 2k plus 1, where k belonging to z, and this will help us to write n is equal to 2k plus 2, and then I can write n square is equal to 4k square plus 8k plus 4, squaring both sides using the a plus b whole square formula, and this will be like n square, and 2 times I can write it 2k square plus 4k plus 2, right? Now from this we conclude what? That since n square has been written as twice of something, and this is nothing but an integer, because if k is an integer, this also will be an integer, so we can conclude that n square is even. So we have shown what? We have shown that P2 implies P3. So we have shown P1 implies P2, P2 implies P3, and third part, because we don't have the space here in the bottom, so I am writing the third part here, that we have to show, that P3 implies P1, right? Now P3 implies P1 means we have to show that if n square is even, then n is even, means if n square is even, then n is even. So to show that, I have to use the method of contraposition, right? In case if you do not understand this term, you have to watch the previous video. So method of contraposition will work. I will take n square is even, and I have to prove that n is even. So what is the method of contraposition? I will start with the statement that let n is odd, means I will start with negation of q, and then I will show that negation of p is true. So I will start with n is odd, and I will show that n square is also odd, and after that we can conclude that P3 implies P1. So this method will work. So we have done it three ways: P1 implies P2, P2 implies P3, and P3 implies P1. Then we can conclude that all these statements are equivalent, right? I am leaving this third part, contraposition part, for you to prove. Next thing that we are going to talk about is called proof by counterexample. Okay, so proof by counterexample is a very powerful method to prove mathematical statement, and this is also very practical application based. In our day-to-day life also, sometimes we face a situation where we judge people based on one instance, right? and that instance may be taken as X instance of counter example. So to understand this, what is the proof by counter example technique? That we know that a statement of the form for all xpx is true if it is true for every value of x. But somehow if we are able to find one value of x for which this statement is not true, then this statement will become false. To understand this, let us solve the second problem first. So suppose we have to prove that the statement every prime number is odd. So if you take all the prime numbers, like if you take 3, 5, 7, 11, 13 and so on, all the prime numbers are odd. But this statement is false. Why? Because we have a counter example. So what I will do? I will write that we note that 2 is a prime number which is even, right, which is even. So the statement is false. Now I have not done anything. I have just given one example which is confirming that this statement is false, right? Similarly, if you take the first example, let us take the first example, that every positive integer is the sum of a square of two integers, right? So sum of a square of two integers. So to prove that, I take the counter example. What is the counter example? That take an integer 3. Now if 3 is an integer, then if I have to write 3 as the sum of a square of two integer, only two integer whose square are not more than 3 are 0 square and 1 square, because if I take 2 square it will be more than 3. But we can clearly see that 3 can't be written as the sum of 0 square plus 1 square. So every positive integer is the sum of squares of two integers is a wrong statement. I hope you got it. I repeat, because if you take any other integer other than 0 or 1, its square will be more than 3. But 3, like if you take even minus 2, so minus 2 square will be 4. If you take minus 1 square will be 1. So if I am taking any integer which are less than 3, whose square is less than 3, there are only two possibilities, 0, 1 or minus 1. So in all cases we can clearly see that 3 is not equal to 0 square plus 1 square, or 0 square plus minus 1 square, or minus 1 square plus 1 square. So it is not a correct statement, right? So that is the process of proving something with the help of counter example, right? So counter examples are powerful ways of proving the statement. The next thing that we are going to talk about is mistakes in proof. And what is the mistakes in proof thing that I can understand by this particular example? Well, so let us proceed with this example. We have to find that what is the mistake here in the given proof. They already have provided us with a proof that we have to identify the mistakes. We don't have to prove it, right? So the question is, what is wrong with the famous supposed proof? So this is not the right proof, this is a supposed proof. So look at the proof step by step. In the left side they have highlighted. So what they are doing, they are starting with that A is equal to B, right? Suppose they are taking A and B as two equal integers. Then in the next step they are multiplying it both side by A. Okay. In step number 3 they are subtracting B square from both sides, because this is a valid operation to do in mathematics, that in step 2 multiplying something in the left hand side, then in the third step subtracting B square from both sides. In step number 4 they are factorizing it, like A square minus B square is being written as A minus B into A plus B, and here b is being taken common and it is written as b into a minus b. In the fifth step, we notice that we have a common term, that is a minus b in the left hand side and a minus b in the right hand side. So we can divide both sides by a minus b, and what we get is a plus b is equal to b. Right. Now as we are already provided in the first step that we have taken a and b are equal, so in sixth step I am replacing this a, this term a by b. So b plus b becomes 2b and 2b is equal to b. Now finally what we are doing in step number 7, that we are dividing both sides by b. So what we are getting is 2 is equal to 1. I hope you got this. Now the question arises that of course we all know that 1 can't be equal to 2. This is a fallacious argument that somewhere we have used. So you have to identify that which step I have made the mistake, or at which stage there is a mistake that is happening in this proof, right? So I would suggest you to pause the video and identify the mistake. Okay, so if you already have identified the mistakes, let me confirm that whether you are able to whether you have been able to identify the mistakes correctly or not. So what is the mistake that we have made, or in the proof of this result that has been made? That in step number 5, in step number 5 we are dividing both sides by a minus b, right? And since a and b are equal, right, since a and b are equal, a minus b will be equal to 0, right? So basically what we are doing, we are dividing both sides by 0, which is mathematically not permitted, right? Or you can even think like this, that we are basically cancelling out 0 from both sides, right? We are basically cancelling out 0 from both sides, and considering this is equal to 1, this is not correct. This is not correct. Dividing both sides by 0 is not a valid mathematical argument. So the mistake that we have made is in step number 5, where we have divided both sides by a minus b, right? I hope you agree to it, right? So please be clear about this thing. Now let us look at one more example where I am using this technique of writing the proof with some fallacious argument, and your role is to identify what is the mistake. So here the proof is for 1 is equal to minus 1. So what I am doing, I am taking product of two integers a and b. So I am saying that a and b is equal to a into b. Okay. In step number 2, I am taking the square root in both sides. So square root of ab is equal to square root of ab. In step number 3, what we have done, we are writing ab as minus a into minus b. So this minus minus will become plus and it will remain ab. In step number 4, we are writing it means removing this square root and writing it separately, that it is a square root of minus a into a square root of minus b. Okay. We know that a square root of minus a can be seen as a into minus 1, and which can be written as a square root of a and a square root of minus 1. So that is a square root of ai. So in the fifth step I have written is it is a square root of a into I, where I stands for under root or a square root of minus 1. And here also we have written it is a square root of b and I, where I stands for a square root of minus 1. Now again we are multiplying under root a or a square root of a in a square root of b, and we are getting a square root of ab, and I into I am getting I square. So in step number 6, we note that we have the situation where a square root of ab into I square is equal to a square root of ab. Now I divide both sides, means a square root of ab and a square root of ab. So I divide both sides by a square root of ab, that will cancel each other. And finally we are getting I square is equal to 1. And what is I square? That is minus 1 is equal to 1. Now what is my question from you here is that you have to identify that where is the mistake happening, because there must be some place where I have made a mistake. I am not answering this question. I suggest you that find the point or find the steps where the mistakes have been made, right? So I think with this we are concluding this lecture, where I have talked about multiple things. We have talked about you know mistakes in proofs. We have talked about proofs by proof of equivalent statement. But before I end, I also want you to solve two problems which I am leaving for you as an exercise problem. So here you can see that a problem statement is given, and for your convenience I already have written it in this order so that it is easier for you to see it. Here also you have to identify that whether this is a valid mathematical proof. I am not saying whether it is valid or invalid. I am just saying that you have to find that whether this proof is correct. If it is not correct, then what is the mistake? And there is one more problem, similar thing that you have to do here also, that you have to look at this and first identify or first decide that whether there is any proof in there is any mistake in this proof. If there is the mistake, then identify at which point or in which step I have made the mistake, right? So with this and I would also suggest you to put the answers in the comment box, that what is your opinion about this, right? So in mistakes I have given you the answer of two of them, and I am leaving 2 or 3 problems for you so that you can think about it, because this is something that requires your own involvement. So that is why I am leaving it for you. So I would expect that you will be putting the answers, correct answers. So what is your opinion about all this in the comment box. So with this I end this discussion. If you are new to the channel, please do subscribe and share with your friends and whosoever is interested in learning discrete mathematics course. This will certainly help them. Thank you and have a great day.